So today we're going to be doing a problem and learning about gravimetric analysis. So gravimetric analysis is a technique through which the amount of an analyte, which is the ion being analyzed, can be determined through the measurement of a mass. So gravimetric analysis depends on the comparing of masses between the two compounds containing the analyte. And the way we're going to do this is that we are going to mix two things that we're analyzing in a soluble soluble water, and then two of them are going to be spectators and two of them are going to be formed precipitate. Let's look at a problem. Alright, so let's look at the question. So at the top of the question, we're given this chart, and it basically gives us the mass of the tablet, the mass of the filter paper, plus the mass of the filter paper, plus the precipitate after several layers of drying. We'll get into why that's important later. And basically what this tells us is that it's mixing this tablet of potassium iodine in water, and then adding an excess of basically lead nitrate into the water, and a precipitate forms. So the first question asks you, for the chemical reaction that occurs with the precipitate forms, write a balanced anionic equation for the reaction. So the way we should start by writing this out is by writing it out as a sum of all of the ions in the equation. Then what we should look for is determine which one of them will remain soluble in the water afterwards. So it will be spectator ions. They're not affecting the reaction, they're not forming a precipitate. But then we look to what's actually going to be forming the precipitate. And we know, based on the rules that we know, that it's going to be lead iodine. So we know it's going to be Pb plus I equals PbI in some form or another. Now we have to balance it. So the oxidation number of lead is 2 plus, iodine is 1 minus, which means there have to be 2 iodine to balance the charges. So then we have P plus 2I minus. So when we're doing this, we add a 2 to the other side of this lead iodine. And that's the answer to 1. And then second, our net ionic equations are useful for these kind of problems because they ignore the spectator ions and instead just have the parts of the problem that we're going to be using for the precipitate reaction, because these spectator ions aren't doing any of the reaction. We don't have to focus on them or look at them. Let's look on to part B. So it tells you to explain the purpose of drying and weighing the filter paper with the precipitate 3 times. So the purpose of drying and weighing the filter paper is specifically that the water adds mass to your final calculation, and you're trying to remove that water mass, because when you get it to almost 0 water mass, that means that you get almost exactly the weight of the precipitate, because the weight of the precipitate is add the precipitate to the weight of the precipitate to the weight of the filter paper, and then you subtract your earlier weight of the filter paper, which was done completely dry. So then secondly, it should be done completely dry. And the water basically makes that measurement less accurate. So then C tells you in the filtrate solution is potassium greater than, less than, or equal to nitrate. Justify your answer. So this one we just have to read the text of the problem, which tells you that nitrate is in excess, which means that there is going to be enough of the lead nitrate and specifically the nitrate, to combine with the potassium, which means that there is going to be less potassium in the lead nitrate. That's just how the text of the problem works. Let's move on to D. So this is our first actual calculation problem that asks you to calculate the number of moles of precipitate that is produced in the experiment. So the first thing we should do is determine the mass of the precipitate. So let's take the mass of the final weighing of the precipitate plus our filter paper and subtract the first weighing of the filter paper, and when we do that, we get 1.698 minus 1.462, and we get 0.236 grams. Then we're going to divide those 0.236 grams by the grams per mole, specifically of this lead diiodine, and what we get is that's 461. We do this little math right here, and then we get 0.236 divided by 461, and that gives us 5.12 times 10 to the negative 4th is the number of moles. Then it says you to calculate the mass percent of iodine in the tablet. So this is a pretty easy problem. So basically the first thing we're going to do is stoichiometry. So we know that there have to be 2 moles of iodine for every mole of precipitate. So we're just going to multiply the number of moles of precipitate by 2. And we get 5.12 times 10 to the negative 4th times 2 equals 10.24 times 10 to the negative 4th moles. But because this is scientific notation, let's multiply or divide this by 10 and then add 1 to the exponent. So now we get 1.02 times 10 to the negative 3rd. Remember, we're maintaining our sig figs. Then we're going to multiply that by the number of grams per mole of iodine. This is sort of the reverse of the previous problem. If you look at your periodic table, you'll see that the number of grams per mole of iodine is 126.91. So we get 1.02 times to the negative 3rd times 126.91. And that gives us 0.13 grams of iodine. But there's one more step. We have to divide this by the total mass of the tablet. You ask, how do we get the mass of the tablet? Well, we just look at the earlier problem. And in the earlier problem, it makes super clear. The mass of the tablet is 0.425 grams. We divide 1.3 times 0.425, and we get 0.306, which is 30.6% iodine. Let's go to F. So F tells you essentially a situation where you have 55 milliliters of water instead of 50 milliliters. It asks you whether this would affect the mass percent of iodine. And the answer to this is no. Here's why. So we know that our lead nitrate is in excess in the original problem, right? And what that means is that the iodine will be almost completely reacted with. As time increases, the amount of iodine remaining in the water will be 0. And what that means fundamentally is the amount of water isn't going to affect the amount of precipitate in the reaction, which means that when we were doing our calculations, none of the numbers that we have are going to change as long as that original number of moles of the precipitate doesn't change, which means no, it will not affect the mass that we get. And specifically, it's asking whether the mass percent of iodine will change, and the answer to that is no. G. So G is a hypothetical where we're using a different thing to form a precipitate. In this case specifically, it's silver nitrate as opposed to lead nitrate. And it's asking you 2 questions. The first part of G says, will this substitution of silver nitrate for lead nitrate result in the precipitation of the iodine ion from the solution? And it asks you to justify your answer. And the answer is yes, because we still have the spectator ions, in this case the potassium and nitrate, but the silver is non-soluble, and it specifically tells you that there is a low value of solubility up in the problem. That's this little K symbol right here. And what that means essentially is that we're going to have a combination of silver and our iodine that forms a precipitate. Second part, it asks you if the student only has access to 1 potassium iodide tablet and a balance that can measure to the nearest 0.01 grams, will the student be able to determine the mass to the nearest significant figure? And the answer is no. So if we look at the problem, we'll see that it has the same number of moles per liter, which means that we're going to get a similar mass. And because the mass of the original problem was less than 1 gram, we can then see that the mass of this one is going to be less than 1 gram. And if we know that it's going to be less than 1 gram, and we can only measure to the nearest 0.01 gram, that means at the most we can get 2 significant figures, which means we can't get 3. So in conclusion, these precipitation reactions are really important because not only can they help us calculate mass percent and understand sort of fundamental ways in which chemistry interacts, but they can also help us determine the identities of mystery particles. And that's a little what I was talking about earlier. Specifically, if we don't know the identity of a part of a reactant, by finding essentially what its mass concentration would be, what its specific mass number would be, grams per mole would be, and then we figure out the rest of the problem, using this precipitation reaction, we can figure out what that is, and that's really the primary use.